Great. Thank you, Mike. And I'm honored to introduce this year's Transportation Science and Logistics Society's Robert Herman Lifetime Achievement Award winner. Warren has been part of my entire professional career. I went back to my dissertation and my first papers, and Warren's work is cited, prominently throughout those. And the thing is that his influence on my work and my thinking has only grown since then. And that is the essence of why Warren is such a worthy candidate for the Herman Lifetime Achievement Award. This is an award that's given to someone who has made fundamental and sustained contributions to transportation science and logistics and has influenced the field through their writings, teaching, service, and nurturing of younger professionals. And at the announcement of the award at last Monday's business meeting, which I think many of you probably attended, Ann Campbell cited the quantitative summary of Warren's career. I mean, this includes 184 peer-reviewed publications, 21,000 citations, an H-index of 70, $48 million in grants, 2 TSL Best Paper Awards, and he's graduated over 60 graduate students. But I want to focus today on the things that really we don't see. And this has brought me back to a 2013 Tristan conference in San Pedro de Atacama in Chile. And I'm certain Warren maybe doesn't remember me there, but he remembers being in the Atacama Desert. It's the driest place on earth, and you certainly experience it when you're there. But at the time, my co-authors, Justin Goodson and Jeff Ullman, and I were deep into what was Justin's dissertation and ultimately a series of papers that were generalizing what are known as rollout algorithms. And this work required us to build a deep understanding, both mathematically and conceptually, of what exactly a policy is. And Warren's book, which you probably all are familiar with, played a really large role in shaping that. And in Chile, I had a really good chance, though, to sit down and talk to Warren. And we discussed, the nature of policies and policy search. And that really helped me refine my thinking on the topic, and ultimately, was part of the inspiration for a paper that Justin, Jeff, and I wrote that provided the framework that generalized these. And the thing that always struck me, right, is that Warren didn't have to do that. He didn't gain anything from it. And the benefit was really only for me and my co-authors. And well, hopefully the field was, learned just a little bit from the paper. But I'm not the only one. Marlon Umer, who just won this year's journal, the best paper for the Journal Transportation Science Award, his paper Dynamic Pricing and Routing for Same-Day Delivery, shared with me the insight that Warren provided as he refined his paper. Marlon wrote, over more than a year, Warren and I discussed both the mathematical model and the methodology of this paper regularly. His knowledge, patience, and persistence did not only lead to a better paper, but also helped me learn a lot in the process. And it wasn't just that sort of one-time thing. Marlon also wrote, for me, it has become a standard in the last few years to ask Warren for his advice and opinion whenever I face a new type of model or develop an interesting method. The last time was just a few months ago. He always helps instantly and thoroughly. I even printed some of his emails and put them on my office walls for research inspiration. And whether it's Marlon pinning Warren's emails to his walls or Justin Goodson keeping Warren's book on his desk where it's regularly open, read, and marked, there is no doubt that Warren has influenced the field of transportation and logistics. So please join me in welcoming this year's Robert Herman Lifetime Achievement Award winner, Warren Powell. Thank you, Warren.
Wow, Barry, that was great. And by the way, you shared with me some things I didn't know, and that was really touching. It's a nice honor to receive this award. When I was invited to give this talk, traditionally people will give research talks on a lifetime of research. And I decided this time I want to bring everybody behind the scenes to help you understand how the sausage was made, because the backstory behind my life career, I did not start off life understanding everything that I do now. So I'm going to go back to my career started while I was a graduate student, 1977 to 1981. Now I was in civil engineering, studying transportation. And in those days, if you were in civil engineering studying transportation, you were studying public sector, cars and buses and things like that. But this was 1980 was when freight transportation was deregulated. And at MIT, there was a tremendous amount of active discussion on the economics of freight deregulation. And I realized that, wow, this thing called the trucking industry looked really interesting. So I came to Princeton in 1981. We didn't have operations research, but there was talk of starting up operations research. In 1982, a former classmate, an office mate of mine, Woody Richardson, was working at Schneider National, which is a major truckload carrier and a real pioneer in the use of optimization. They started everything as far as analytics in truckload trucking. And Woody recommended this supervisor meet me during an East Coast trip. So a supervisor had a master's in operations research, and he knew that all of the models being used at Schneider were deterministic. Truckload trucking is very random. It's very last minute. And he said, look, Warren, the problem is stochastic. And he wanted to know what type of a discount they could give to shippers that the shippers would provide more advance notice. And all I remember is sitting there over dinner going, what a great question. Not only did I not know the answer, I didn't even know how to think about it. So this started a lifelong journey. So let me give just a real quickie introduction to truckload trucking, because one of the beauties is how easy it is to describe it. You've got drivers, you have loads, you have to assign drivers to loads. It's a lot like Uber, but we didn't have Uber back in those days. And this evolves over time with a lot of random phone calls of new loads and drivers arriving late and things like that. This is a graphic we did of the freight flows from Schneider National. It's a long haul carrier. By the way, it's much bigger than it was here. Back in the early 1980s, they had about 300 or 400 trucks, which was huge by those standards. But the main operating question is which load should be served? Because any truckload carrier will get phone calls for loads out of, say, St. Louis. And, you know, from day to day, you might have 2 trucks, you might have 5 trucks, you might have 8 trucks. So it depends on how many trucks you have. And you easily may get requests for more loads than you have drivers. So you have to pick which loads. And then you have to pick which driver. Like I have a load going from St. Louis to Massachusetts. I'm sorry, I have a little distraction here of my dog. Excuse me.
Classic virtual, right?
Yes, this is typical things that go on behind the scenes. And so, like if you have a load going from St. Louis to Massachusetts, do you put the Texas-based driver, the guy whose home is Texas, or the one from Chicago? And there's a lot of operating constraints. Now, this graphic has to be the oldest graphic on my computer. It's almost as old as PowerPoint. This was the diagram that Schneider National would use, and they would have locations. They would divide the country into about 100 to 120 regions. And you have time, space and time. Time would move forward in about 4-hour time steps. Solid arcs were loaded movements, dashed arcs were empty movements, and they would plan about 7 days in the future. And the beauty here, remember, early 1980s, we didn't have Gurobi and Cplex, but we had network simplex, and everybody was coding up their own network simplex. And as long as you had just moving trucks and all trucks were the same, this is a pure network, and you can solve it with network simplex. So this was sort of our foundational model, but I wanted to do stochastic. So at MIT, I had a course in dynamic programming, and we learned about Bellman's equation. And so that was Bellman's equation. So there I was scratching my head going, okay, so, well, let's start with this. And I had a Greek student. I had him reading Marty Putterman's wonderful book. Now, just sort of an idea. Let's pretend that we have the 48 lower continental states, and a truck can be in the state of Texas, and then moving around from state to state. I'm having a lot of fun with the word state. Now, the challenge here is if you have one truck, let's say I divide the country into a 5x5 grid. So I have 25 zones, and we could call that 25 states. So if you have one truck, you can be in any one of these 25 states. But if you have 2 trucks, you start now having all the combinations of 2 trucks. And if you have more than 2 trucks, well, that starts to get really complicated. You can have multiple trucks in the same zone. I worked out a formula. Don't ask me to derive this now, but the number of states is the number of trucks plus the number of regions minus 1, choose number of regions minus 1. So if you have 5 trucks and 100 regions, which is fairly typical, you would have 91 million states. If you have 50 trucks and 100 regions, you have 10 to the 40th states. That's not the big number down there. I don't know how big that one is. That's the next to the bottom line. And by the way, truck drivers are more complicated than just being in a physical region. They have a number of attributes. So I spent the 1980s trying all different ways of modeling these problems. I tried deterministic networks and Markov decision processes. I had all kinds of fancy nonlinear programming approximations, stochastic programming, and none of them worked. And I wrote them up in what I now call my museum paper, because it really belongs in a museum. This was every method that I knew how to model these problems. And the worst is just all of them were clearly wrong. I mean, you know, we could publish papers with this stuff, but to actually go to the field and model a real problem, nothing came close. So this was me in the 1980s, just thrashing around. 1990s is when I established Castle Lab. In 1990, I hired my first PhD student, Hugo Simeo, who was with me in the early 1980s. Went back to teach in Brazil, returned, and we had landed this very large project with Yellow Freight. And we started taking on serious software development projects. This is when I learned that I needed to fire myself as the #1 programmer in my lab, hire these professionals, and I ended up hired Hugo in 1996. I hired Belkacem out of University of Montreal. At one point, I had a total of 4 programmers. And in 1993, very key, I began 28 years of virtually continuous funding from the Air Force Office of Scientific Research. And in the 1990s, they really enjoyed when their people they were funding worked with the Air Mobility Command, which is just a different type of fleet management problem. It's just that it flew around. So the 1990s, I actually took on a wide range of projects. My biggest one was this one with Yellow Freight, at the time, the largest LTL carrier. I think maybe it's now the second largest. Roadway Package System, which is now FedEx Ground, a couple divisions at North American Van Lines. Burlington Motor Carriers was a small truckload motor carrier, but it was one of the rare truckload motor carriers that would actually fund projects at Princeton. I worked extensively with Norfolk Southern Railway, mainly on locomotive optimization, Triple Crown Services, which was drayage, Air Products and Chemicals, which is a provider of industrial gases, and Embraer, which is a Brazilian aircraft manufacturer that had a nice problem of high value inventory parts. Now, because I was solving such a wide range, and because I'm not a company, I couldn't run around and just take on competitors. I couldn't take on a whole list of companies all doing the exact same thing. I had a tremendous amount of variety. And one of the challenges was just how to model them. And I didn't know how to model them. And every time I had a student work on one of the projects, I had one of these awful periods of, oh my gosh, how are we going to model this? And in the late 1990s, I spent about 2 solid years working on this modeling paper. And I knew that I was probably the only person who was going to ever read this. I call it my Uber modeling paper, but I introduced some really key concepts that I still use this day: multi-attribute resource layering, the evolution of decisions and information, and a few other things. And so this became my language, where every time I would sit down to a new resource allocation problem, I would draw on that. Now, one of the major projects that I started in the late 1980s was a network design model. It was an interactive optimization model that we did for Yellow Freight. They called it SysNet. We ended up, started my first company, Princeton Transportation Consulting Group, and they marketed it as SuperSpin. Now, starting at 1990, Yellow gave me a very large project to optimize the drivers. So even though it's LTL trucking, the driver side was more like truckload trucking, because you had these trailers full of LTL freight, but then you have to optimize the drivers. So here's a very nice graphic of the drivers. I've used this graphic many, many times. The colors refer to driver domiciles. And basically what happens is a driver has a domicile. They generally move west, and then they have to return. So they move west, usually spend the night, return the next day. And so this was a union carrier, as it still is. And my problem was how to optimize these. Well, I started with the same model that we use for Schneider, but now it's multi-commodity flow. So whereas in Schneider, we just sort of pretended that all the trucks were the same. Now I would divide every driver by domicile as a different commodity. Now this is a network of about 800 terminals and about 40 driver domiciles. So imagine having 40 copies of this network that had 800 rows instead of Schneider's 100. This model was way bigger than anything that we could solve. And the irony was, I could still see that we were missing key features, such as the ability to model the driver's DOT hours, his hours of service, and that sort of thing. So this is a hyper-large integer multi-commodity flow problem. And I just looked at it and said, okay, we're not even close to doing this. Now, I was working down at Yellow in their central dispatch office called CDO, and wondering how in the world does this group of people, mostly with high school educations, solve this problem? And I realized, oh, they're not optimizing over a whole week. They're just greedily optimizing, but they are looking a little bit into the future. They understand that when you send a driver from A to B, that they now have a driver at B. So I said, well, what if we just capture the value of this driver? And then the thought occurred to me that when we have drivers at a location, it's almost like a double-ended queue like you see in taxi cab stations. And I was actually at waiting for a cab in the Washington, D.C., and we had a long line of people and a long line of cabs. And I'm like, wow, this is kind of what it's like, at least with Yellow Freight, because you have these truck terminals with long lines of drivers and loads. So I called this a logistic queuing network. So now we have a much smaller problem of assigning drivers to loads. You're going to see this graphic repeatedly. And then I have the value of the driver in the future. Now, what you can do with this is to form a relatively simple linear program of assigning drivers to loads where you have the value of drivers in the future. This whole problem is a linear program. It doesn't go 7 days in the future. It's all pretty much here and now because these V's are what's approximating the future. So I'm like, wow, this is really cool. In fact, this almost sort of looks like Bellman's equation. But there's Bellman's equation at the bottom, and okay, it sort of looks like Bellman's equation, but not quite. For example, there's that expectation. And I know this is a stochastic dynamic problem because random things are happening, but I didn't know where to put the expectation. And by the way, if you put an expectation in that linear program, now I can't solve the linear program. So I really was struggling. And you have to understand that when you figure it all out and you put it on a sheet of paper, it looks easy. But there was years where I was staring at this going, I don't know what I'm doing. I don't know how to get this to Bellman's equation. So in 2002, I attended a workshop organized by NSF Program Director Paul Herman, who, by the way, was an early pioneer of approximate dynamic programming. Back in those days, they called it various names like heuristic dynamic programming. He came from the controls community, and he had a workshop on approximate dynamic programming and reinforcement learning. So all the people from computer science called it reinforcement learning, and apparently everybody else was calling it approximate dynamic programming. I had been calling it adaptive dynamic programming because you learn the V's adaptively. I've got a whole series of papers with adaptive dynamic programming, but at this workshop, I realized, oh, okay, I guess I need to call it approximate dynamic programming. Well, they wanted to do a volume off of it. And Ben Van Roy from Stanford, who was an early pioneer of reinforcement learning, was there, and he didn't want to write a chapter. And I said, Ben, co-author my chapter with me, because I wanted somebody to really take a hard look at what I was doing. And he did, and he realized, oh, this is a concept that he introduced a few years earlier called the post-decision state variable. And that was my aha moment, because I'm like, oh my gosh, that's the right term. So here's the little example. This is actually Ben's example. You take a simple inventory problem where R is my inventory of resources. That's my state variable. And X is my decision to order more resources. And then D hat is the random demand. Now look toward the bottom. I've divided that inventory equation into two steps. One is that I'm going to add X to R and call that the post-decision state. That's the state after you make a decision, but before any new information arrives. And the one thing that I sort of introduced was to do the time indexing, because Ben and the RL community does everything in steady state. So that first line, you have the pre-decision state RT, which is what everybody calls the state variable, add in X now that you have the post-decision variable. So I said, okay, I still need to use the same variable R and I want to index it by T, but I'll put a superscript X to say, oh, that's the post-decision state. And then you have a different equation that takes you from post-decision state to pre-decision state. Now, this looks obvious when it's on a sheet of paper after you figured it out. This was agony. And it was Ben's term of post-decision state that I realized, okay, that's it. That's the right word. This is how to do it. So now what we're really doing is breaking Bellman's equation into two steps. First, we have the value function, the post-decision value function around the post-decision state. And that gives me a max problem that's deterministic. Well, that's cool because all I need now is to have the right form for a value function, say a linear approximation. And now that's an easily solvable linear or integer program. I can use standard commercial solvers. Now to get from post-decision to pre-decision, that's just an expectation, no max operator. So this is what opened the door to solving dynamic programs where the decision was a vector and a big vector, the world of operations research. Now, the expectation we handle using Monte Carlo simulation methods, and this was suddenly, okay, now I've got it. So now what I've got is that same linear value function. Notice that the notation is a little bit different. Indexing things at time t, not t plus 1. I've put the superscript x, but it's still the same linear program that's easy to solve. Now, what you can do is, let's take that set of drivers at time t where I'm matching drivers to loads, and then I have downstream values, so I don't have to optimize over 7 days. It's just at time t plus a value function. Now you simulate the value function, coin flipping as you need to. And by the way, here I can model things at a very high level of detail. Now you do iterative learning, and you can do these dozens or hundreds of times, but it's through this, which is how you learn the value functions. Here's an actual chart from the startup company that I now work with, Optimal Dynamics. This is the results from 11 different trucking companies showing over 15 iterations the steady improvement in the objective function. So it's very different from company to company, but you've got this steady improvement. Now, here's an actual simulation for Schneider National. We're modeling every individual driver. We're modeling their hours of service. I know their domicile. I know their equipment type. So this is basically an optimizing simulator where you can do all the things that people do inside a simulation. So this is what laid the foundation for my ADP book. This book introduced things like the curses of dimensionality. There's 3 curses. Most people doing dynamic programming use scalar action variables. And of course, coming from OR, we've got our usual vectors of resources. But there are 3 dimensions, the state variables, 3 multidimensional variables, the state variables, the decision variables, and whatever's random. I call it the exogenous information. And I also have a dedicated chapter 5 that all it does is model. And it breaks the modeling down into 5 components that I'll show momentarily. And then also in this version, this was the 2nd edition, chapter 6, I talk about 4 classes of policies. And I didn't get them right, but I at least had the right thinking. Now, one of the things that you do, if you do approximate dynamic programming, one of the first things you learn about is something called the exploration versus exploitation problem. So in trucking vernacular, it would be like, if I want to know the value of a driver in region J, you have to visit region J. You've got to send the driver to region J. And region J might be terrible, but I don't know until I visit it. So in other words, if all I do is use the value functions as they are now, I'm exploiting. But if I send a truck to a region that maybe is a bad region, but it might actually be very good, that's what we call exploration. So the exploration versus exploitation problem is tied to this wonderful story called the multi-armed bandit problem. This is where we pretend that all the slot machines have different winning probabilities. So think of these as, well, 7 different options where we have different performances, and I have estimates of how well each one works, but I have uncertainty, sometimes high levels of uncertainty. So that choice number 2 doesn't look to be the best, but maybe it is. Maybe I just have to try it. Now, the standard bandit problem you learn as you go. I had gotten involved in the problem where you had a bunch of iterations. I have 15 iterations to learn, and I have to do the best I can in 15 iterations, but all I care about is how well I do at the end. That's called offline learning. So I started working on this with a graduate student at the time, Peter Fraser. Peter started to come up with some ideas. We had to simplify the problem quite a bit. The original problem of moving trucks around to really understand the exploration versus exploitation problem is actually quite difficult. So we kept simplifying. We got it down to this multi-arm bandit style. And Peter came up with a policy that he just called the myopic heuristic. It was a one-step look ahead, but it worked really well. And he could prove some really cool theorems. So I said, okay, Peter, this is really cool, but we can't call it the myopic heuristic. So we ended up calling it the knowledge gradient, because it's literally the marginal value of information from one experiment. Well, that just launched this whole line of research that I ended up calling optimal learning. It was the foundation of about 11 different PhD students, but my first two, Peter Fraser and Ilya Ryzhov, really laid the foundation. And it also led to a major Air Force project on, wait for it, material science. And suddenly all my work in trucking, which didn't stop, talk about a career detour, and I won't go into the full details of how I landed in this, but suddenly I was doing slides like this with all types of fancy molecules and stuff. That picture in the middle is a robotic scientist, and they needed an algorithm that would tell this robotic scientist what experiment to run next. So the graphics to the left there, we built the knowledge gradient. So the one furthest to the left, blue is a really cold region, you don't learn anything. Then red is really hot, you learn a lot. Notice the blue region corresponds where you learn the least is where things work the best according to our current beliefs. So we had a lot of fun with this. I met a really nice group of people, very different. It was interesting talking to people, what I call really smart people who know very little mathematics, or at least very little mathematics about probability, statistics, and optimization. Now, I ended up realizing this would be fabulous material for an undergraduate course, because the problems are actually relatively simple and they arise everywhere. So I have a website, castlelab.princeton.edu/ORF-418. I started working on a second edition of the book. You can download the second edition from the website. And boy, if you'd like to do a course on optimal learning, let me know. Now, I still am an OR person at heart, and I never really gave up working on my resource allocation problems. But the optimal learning detour really taught me about belief states. Now, I want to show you two pictures. Here's a graph. Everybody in transportation knows about a graph. And so let's say I'm at node 2, that's my state. And I take a decision to move to node 5. And so now I'm in node 5. And we know that we can set this up using Bellman's equation. It turns out you can do the same thing with our learning problem, where the state right now is my state of knowledge. It's all my estimates, my means and variances. So my state variable, if I have 5 choices, I will have 2 parameters per choice. I'll have a 10-dimensional state variable, by the way, continuous states. If I choose an experiment to run, let's say I run experiment number 5, and then I learn something that takes me to a new state, you can still set up with Bellman's equation. And this is my aha moment that says, beliefs about problem are actually no different than a physical state, like an inventory or the location of a truck or where you are on a graph. So you have to pull, in other words, state variables are information or knowledge, physical states, information states, belief states. And I took that into my work that I was starting to do in energy. Here's a little example from my energy work. A few years ago, New Jersey got hit by Hurricane Sandy, catastrophic hurricane, really terrible. We had power poles down all over the place. And this is where I learned that when a utility pole goes down, the utility doesn't know where it has gone down. They have to literally drive trucks around discovering this. So here we have a setting where we have utility truck that has a physical state. The physical state is where is the truck. I have other information. This is people calling in that their lights are out, or there's weather information or flooding. And all those fractional numbers are probabilities that there might be an outage there. And that's my belief state. So I have physical state, information, and beliefs. And that is my state of my system. Now, here's another problem that I worked on with Lei Zhao at Tsinghua. This was an e-commerce problem where you have zones and you have to allocate a certain number of trucks per zone to do all the deliveries. And the problem is, what's the right number of trucks per zone? Now, Lei was doing this in a simulator, And so what we would do is every simulation, the simulations were quite expensive, we would try different allocations. And this is an optimal learning problem where the only state variable is my belief about what is cost as a function of the number of trucks per zone. And every zone has its own cost curve. And we had to learn this. But imagine that you had to do this in the field, that you're a real e-commerce company and you don't have the money to build some simulator. So you have to do trial and error. And now you have a physical state of where the trucks literally are. And if you want to try a different allocation, you have to literally move the trucks. So now you have a physical state and a belief state. Now, somewhere around the mid 2000s, I had a bit of a midlife crisis going, okay, I've done a lot of trucking. Let me look around and see what other problems I might work on. I really enjoyed energy and health. If you're at Princeton, and you want to do health and operations research, don't come to Princeton. We don't have a medical school. We don't have a teaching hospital, but energy was really hot. They were starting a new analytical energy center. Suddenly, you just had to shake the trees in those years to get energy monies. I don't think it's true today, but boy, in those years, you just had to say, hey, I'm interested in energy, and money started flowing at you. I set up the Princeton Laboratory for Energy Systems Analysis, or PENSA, and I took my trusted colleague, Hugo Sameo, and we started writing energy models. So here's the PGM grid. We have nuclear power plants, steam generator, gas turbines, all types of renewables that were mostly made up and simulated. And we did stuff with demand response. Now, we would model wind. Wind has its own spatial distribution. It has a temporal distribution. You can see wind sort of dies down in the summertime. And it's also pretty variable hour by hour. Solar also has a spatial distribution. Most of it's down there in the Southwest. Sorry, my friends there. But it turns out politics do matter. In New Jersey was really excited about solar. And so they were putting in aggressive programs to encourage investments in solar. Now, this is solar out of a set of solar farms in New Jersey over the year. And you see that sun doesn't shine as much in the wintertime. So it sort of complements the wind dying in the summertime. But of course, we know that solar has this other behavior. It sets at night. And you also have cloud cover, and you see this variation due to cloud cover. Now, we worked very hard doing modeling of the PGM grid and everything that they did. And we applied pretty much all our same skills that we developed working for trucking companies and railroads. We had a very detailed model of the decision-making process. We had an AC power flow model, which if you're not into energy, maybe somewhere in your engineering days, you remember the difference between AC and DC. And by the way, AC is hard. And we did really good job with stochastic modeling of wind and solar. Now, one of the things with energy planning is you have all types of decisions. You have day ahead planning, hour ahead planning, real-time planning, and you really have to model these lag decisions. And this is where things get really hard, because if you're sitting at noon planning energy generation tomorrow, you've got to realize that you're going to have decisions every hour, every half hour, every 5 minutes. And one of the things I really had fun with, some frustration, the energy sector, which is very heavy with engineers, has a real problem with uncertainty. And Princeton's engineering school at one point decided they wanted to do cartoons of people's labs. And they decided that they were going to make me their first cartoon. And I said, I don't want a cartoon on my research. I want a cartoon about uncertainty. And my favorite panel is this one where the customer's pointing up and saying, oops, the sun just went behind a cloud. And the utility saying, we needed to know that yesterday. And I love this panel. I don't care about the rest of the cartoon, because this is the essence of why uncertainty is important and hard. Now, in the process of working with energy, I found that they did a lot of what a lot of people do. They plan in the future deterministically, but they put in tunable parameters to allow for uncertainty and that sort of thing. And I was surrounded by substantial groups of people using stochastic programming with scenario trees. And they all thought, oh, to handle all this uncertainty, you need stochastic programming. And after spending a lot of time with Hugo calibrating this model and tuning it, I came to the conclusion that the scenario trees were fundamentally flawed. And what industry was doing was actually a really good idea. And what they were missing was fancy words and fancy math. So I came up with the phrase, the parametric cost function approximation. If I were starting my career today, and if there's any young people out there looking for something to do, please take a look at this. I've got a website set up just to explain it, tinyurl.com/CFA policy. It has a copy of paper with my previous postdoc, Saeed Kadimi, where we took an energy storage problem, but a particularly hard one, and used the idea. This is what you do when you do a deterministic look ahead, and then you throw in tunable parameters to make it work better. So you have a parameterized deterministic model, and it's really effective. It's way more effective than stochastic programming and scenario trees. Now, this is a problem this is an energy storage problem we had a tremendous amount of fun with. I've got a website set up with about 24 different papers, energy storage, which is just an inventory problem, but it's a very rich type of inventory problem. We even extended this to grids where we'd have, and this was ADP, I would have a value function for the energy in each battery. We would use the same techniques we did for transportation, but now it was energy in a battery. We would do the same type of learning to learn the value functions. This is the plot of a grid at a particular point in time when there's high levels of congestion. All those reddish rectangles are very congested links. Now, the blue and green dots are places where there's energy storage, but I'm not using them in this run. But after running ADP, and where we've started putting energy at the exact same instant in the simulation, you can see that we've largely cleaned up the energy storage. And by the way, you can't choose not to cover demand. In energy, you have to cover all demand. Demand is completely inelastic. So we're covering all demand and avoiding the congestion. Now, here's another problem we're all familiar with, Uber. Now, this was actually an energy project because we took over the problem of, we jumped on board with the, okay, we're going to have driverless fleets of electric vehicles. So we took an Uberish type of problem and some data from Uber. Now, Uber's got this other issue of pricing. They have to jiggle the price to balance drivers with riders, because if the price is too high, they don't get riders, and if the price is too low, they don't get drivers. So they have to balance it, but they don't know the trade-off. And guess what we use to represent that? It's a belief state. I have uncertainty about what curve is correct, and I will have a probability distribution on these curves. Now, we just did the same work that we did for trucking. We just have the value of drivers in the future. Here I'm assigning driverless cars to riders, and we have the value of cars in the future. It's just that this time the value functions are very different. The main attribute of a car, other than time and location, is the stored energy level of the battery. And I would have to look forward and get this curve. And you can see that this surface is not pretty. It's complicated. But we drew on some of our same techniques from the trucking side. Now, we did a study of New Jersey. This is a 24-hour period. This is the peak period in the late afternoon. Now, that red line is the aggregate amount of energy in all the cars. And you can see that there's a period where the energy is going up. That's because I'm charging. Now, here's what you don't want to do. You don't want to charge during the peak period. Now, the simulation on the left, we were just using simple rules, like if I get below 10% storage in the battery, I have to stop and recharge. So it's a very simple rule. Now, on this side, we used ADP. And notice that during the peak period, I'm mainly declining. Okay, that energy curve is not going up. It actually goes up in the off peak, just before we get to the peak. So the ADP was smart enough to learn, I don't care what level of charge that you have. If it's off peak right before the peak, head into a station if you can and get charged up. So that was cool. Now, this slide is sort of this is my life. Every one of these rectangles is a problem that I've worked on. And I've worked on a lot of different problems. And over the course of the experience of working on this wide range of problems, you develop sort of, being academics, I develop a sort of a general way. Now, about a year ago, I put together a picture to sort of highlight in a pretty graphical way all the different problems I've been working on. This is not all of them, but you get the idea. It's quite a wide diversity. Now, every one of these problems has decisions. And so what I did was I put a couple boxes behind every single picture with an example of a decision that had to be made. Okay. And one of the things about these decisions is every time I make one of these decisions, new information arrives. And this is information that I didn't have when I made the decision, which means all of these problems have decisions that have to be made under uncertainty. And so in a community like transportation, where so much of the work is deterministic, it's amazing how we're surrounded by problems where you have these sequential decision problems with new information coming in. Now, the biggest problem that I've struggled with most of my career is how to model these. Now, if you have a deterministic problem, nice thing is everybody doing deterministic optimization knows how to model it. It goes back to the 1950s, and we can get papers from around the world, and they all understand the language of George Danzig. But once you get to these sequential decision problems, we don't have a standard format. In fact, we have a real mess. Every one of these terms is actually a different field. It's different communities working on different types of problems. They have one or more books. The optimal control, there must be at least half a dozen books on optimal control, several books on Markov decision processes, and so on. And there are about 8 different, fundamentally different notational systems. There's some dialects and accents. There's a wide variety of different algorithms, and there's also wide variation in the types of problems people solve, from low dimensional to binary problems to these high dimensional resource allocation problems. So the last 10 years of my career, starting in 2011, which is when the second edition of my ADP book came out, I have 2 chapters that I actually have posted on an internet site. I make these freely available. Chapter 5 is just how to model. And it introduces the 5 elements of the sequential decision problem. And then chapter 6 says, oh, and there's 4 classes of policies. Now, I didn't get the 4 classes right. I got 3 of them right, but not all 4. In 2014, I was invited to give a talk in the Informs tutorial series, and you have to write a chapter for that. And I called it Clearing the Jungle of Stochastic Optimization. This was the first paper to introduce all 4 classes of policies. By the way, I still have the referee report that says, oh, it's not so bad. It's not a jungle. You should call it Clearing the Garden of Stochastic Optimization. One of these days, I'm going to start sharing some of the referee reports that I've had to live with. So 2016, they invited me back, and so I wrote another chapter, but this time I cleaned up some of the mistakes in the 2014 article. I realized the 4 classes of policies fall into 2 broad categories. And then around that time, Roman Slowinski for eJOR invited me to do what they call a review article, and I wrote my final unified framework paper. And this is the paper where I really nailed a number of other issues, such as offline and online learning with final award and cumulative award and a few other things. It's really quite a good paper. It laid the foundation for my newest book that is called Reinforcement Learning and Stochastic Optimization, a Unified Framework for Sequential Decisions. And by the way, the reinforcement learning and stochastic optimization in the title is there just to grab Google searches. But I've also put together a website on sequential decision analytics. If you go to tinyurl.com, SDA field, really encourage you to go to that website. Now, let me tell you how to model sequential decision problems. You have a state variable that has everything that you know or believe. You have a decision that you make, and then you have new information that arrives. Each time you make a decision, you receive a contribution or incur a cost that can depend on the state variable. Decisions are made with a method that I call a policy, which is also a pretty standard term. And I use capital X pi, but you use capital of whatever variable you're using for a decision variable. And now the goal is to find the policy that maximizes expected contributions. Now, it turns out you can boil down any sequential decision problem into these 5 elements. State variables, decision variables, exogenous information. The transition function tells you how to get from a state, then you make a decision, then you observe new information. It tells you how to get to the next new state. And finally, we have an objective function. And then these can come in different styles. I use the most common style, but there's a few variations. But these 5 elements describe every one of the books in the jungle for stochastic optimization. Now, for those of you who mainly do deterministic optimization, there you go on the left. It's a time states problem, but this is your classic formulation of a deterministic optimization for a problem defined over time where you're minimizing over X and your decision variables are the X. When you do stochastic, notice how you have, I like to maximize, so I maximize over policies, an expectation, and then inside the summation, I don't have any X's, I have the policy X pi. So this is if you do deterministic and you want to do stochastic, you just go from the left side to the right side. Now, I'm particularly proud. So using this framework, we've got a couple of TSL Best Prize awards that came out of my lab in 2010 and 2015. But I am really proud of a paper I didn't write. This is Marlon Ulmer's paper that won the Transportation Science Journal Paper of the Year Award. I helped Marlon. I was sort of a managing editor. I was not a referee, but I was sort of helping and giving some edits. I'm very appreciative of his acknowledgement, but not so much of me, but I really focused on, and the author highly recommends studying this framework. Now, if you go to chapter 2 of my new book, you'll see that I give due credit to the field of optimal control, believe it or not. Most of my framework comes out of this. Now, if you go over to computer science, they are very proud of their ability to optimize computer Go. And hey, I'm pretty proud of the fact that I can model and solve this fleet of 5,000 trucks. And I got to tell you, I didn't get as much visibility as the computer scientists get, but I think that's a pretty neat effect. And by the way, Marlon Ulmer's paper was a very complex problem in e-commerce. So I want to show you something. Here's machine learning. So machine learning is really hot, and we all sort of understand it. This is where we're trying to find a model to fit data. Let's say I'm trying to do demand to fit as a function of price. And somebody comes in and says, oh, it should be a linear function. I actually had an e-commerce project where somebody did this. And so, of course, you want to find the best linear fit, but somebody else may come in and go, oh, you don't want to do a linear fit. You want to do some sort of a nonlinear fit. It's more realistic. And of course, if I do a nonlinear fit, I want to do the best nonlinear fit. Nowadays, somebody's going to come rolling in and saying you should do a neural network. Word of caution, neural networks can do a lot of overfitting. But the main thing is you're looking at different types of functions that come in 3 broad categories: lookup table, parametric models, and non-parametric. So here we are trying to search over functions and then any tunable parameter within that class. And I need a big data set in order to fit the function. This is machine learning, supervised learning. So if you compare machine learning, you're searching over functions, statistical models, and you have the 3 major classes. In sequential decisions, you're also searching over functions. It's just we call them policies. Now, in machine learning, you need a big data set to fit your function. But in sequential decisions, you don't. You need a model, okay? And so this is sort of the key difference. And so we're very similar to machine learning. The main difference is we don't need the big data set. We need a model. So here's the question: how do we search over policies? Now, normally in these talks, I give a real 20-minute presentation on these classes of policies. Because this is a story of my life type of thing, all you're going to get is one slide. So we have 2 broad categories. There's the policy search category, where what you're trying to do is to find the best policy within a class. So the policy function approximations are some type of analytic function. It can be an order up to, buy low, sell high. It can be a linear decision rule. It can be a neural network, but it's some analytic function that maps state to action. And the cost function approximations, which I've already talked about, it's some sort of parameterized optimization model. So it's just like the PFA, which is all parameterized functions, but now I'm going to cheat a little bit. I'm going to actually create, say, a deterministic optimization model, throw in some carefully chosen tunable parameters, and then tune them. And then we have the look-ahead policies. These are policies where I make a decision by approximating the downstream impact of the decision now. One way to approximate it is with a value function approximation. So that upper right-hand corner box, that's the world of ADP and VFAs, and by the way, the earlier world of reinforcement learning. And then down below, we have the direct look-aheads. Now, I want everybody to go to the Jungle website, jungle.princeton.edu, scroll down until you see this picture, print it out, put it up on your desk, tape it. It's got the way you should do objective functions, which is min or max over policies. It's got the 4 classes of policies, because all of us do sequential decisions. And when you make a decision, I guarantee you're using one of the 4 classes of policies. In fact, I claim the 4 classes of policies are universal. They cover anything that you might use. Even if you never read my book, you're going to use one of the 4 classes of policies. Now, let's come back to our comparison of machine learning and sequential decisions. The policy function approximations, turns out, includes all of the functions that we use for machine learning. So the PFA class is lookup table, parametric, and non-parametric. The remaining 3 classes are all some form of optimization problem. So searching for policies and sequential decision problems It's got similarities with machine learning, but it's much richer and it's harder because you've got the modeling dimension. Now, one thing that I caution everybody makes sequential decisions. You're already doing it. Every company does it. So it means they're using one of the 4 classes of policies, maybe a hybrid. Most people use policies in the policy search class, okay? Or look aheads with a deterministic look ahead. Those are the 3 broad classes of policies I think are most popular. The policy search class are the simplest. It's what you're going to most likely see used in practice. But as I like to say, the price of simplicity is tunable parameters, and tuning is hard. First of all, to do tuning, you have to understand what the objective function is. So here's my favorite little energy storage problem. We really had a lot of fun with this. At one point, my postdoc, Stefan Meisel, put together 5 different variations of that same problem. We just played with the data. We would make things more or less stochastic and steady state or time varying. And we came up with 5 policies, the first 4 being from each of the 4 classes, and the 5th one was a hybrid. We made each of these 5 policies work best. So I claim you really do have to know about all 4 classes of policies. And I'd really like to see schools start teaching courses in sequential decision analytics where students at least learn the 4 classes of policies. So I get a lot of questions about which of the 4 classes of policies we should use. I'm going to give links to my book, but it's right here in the lower left-hand corner, tinyurl.com, RL and SO. Chapter 11 is dedicated to reviews of the 4 classes, and I've got a whole section on how to choose among them. It's a little bit messy. It depends on the problem, but there is a trade-off. Especially when you have more complex problems, if you try to do a simple policy, it's going to be harder to design. You can have more complex policies that are harder to compute, but it turns out they're more brute force in terms of formulating them. So there's a more natural pathway on how to create the policy. So we live in a community that has core disciplines of decision analytics consisting of optimization, machine learning, and simulation. And you can go to most schools, take a course in any one of these 3 areas. You can use any one of a number of textbooks, and you will walk away roughly knowing the same thing, okay? Books can be a little bit more tuned, but these are well-defined communities with well-defined concept notations, vocabularies. Not true with sequential decisions. Sequential decisions is a complete mess. You can get, and by the way, most of these books are aimed at advanced PhDs, people with strong methodological training, whereas there's a lot of fields where, industrial engineering, civil engineering, mechanical engineering, a lot of electrical engineering, chemical engineering, social sciences, politics. I had a graduate course. I had students from 8 different departments. And they all have good problems. They all have sequential decision problems. What they tend to do, but they don't have books that really cater to those communities. I wrote a more introductory book for an undergraduate course. You can download it from SDA Intro, or tinyurl.com, SDA Intro. I'll be publishing this book. It needs work. So this is very much of a rough draft, but it uses, most of the chapters use a teach by example style. This is my new book. You can go to tinyurl.com, RL and SO. It should appear, I'm told, May 2022. So it's in press as we speak. I'm still trying to get the last typos and word edits out. But it covers the whole range of sequential decision problems. I really encourage you, download chapter 1. Just please download chapter 1 and give it a read. This was a lifetime in the making. And one of the reasons why I did the slide showing all the wide diversity of problems is after being Mr. ADP, and you have no idea how many people think I'm solving every problem with ADP. I don't. I actually don't use ADP very much. Most problems, you're going to be using the other classes of policies. ADP it's a very hard technique for very hard problems. This book gives all the fairly balanced treatment of all 4 classes of policies, although there are more chapters on approximating VFAs than the other ones, but I try to give a very balanced presentation, and when I talk through people in chapter 11 about how to choose a good policy, I think it's a very balanced presentation. I also differentiate between what I call the learning problems, chapters 5 and 7, derivative-based stochastic search, derivative-free stochastic search. Now we've taken this into my son's startup company, Optimal Dynamics. Optimal Dynamics licensed all of my truckload code. It just had a very successful Series A rounding. It's raised about $22 million in funding. It was led by Bessemer Venture Partners, which is one of the oldest and most prestigious of the venture capitalists. Now, if you would like to, once again, I have a white paper that I wrote. It's a technical white paper. It has math. And even if you don't read the white paper, just read the section headings and you will see discussions of all 4 classes of policies. If you're an academic, you can be Mr. ADP or Mr. Stochastic Programming, but when you go to industry, you've got to have the full toolbox. So, just take a peek at, even if you just look at the section headings. I do have to close out a career with many, many thanks. I've enjoyed a lot of funding from government. I don't know, about 42 different grants and projects. Air Force has been particularly nice because it's much easier to get continuous funding. Industry's been fabulous. I've had to work with a lot of companies that coined the term the bleeding edge. And that's the term that they use where at the end of the project, it doesn't work. So I've had some projects that didn't work. They were great learning experiences. But the fact that these companies were willing to come to me, these projects were funded at Princeton University. They funded programmers and graduate students. And they shared data and they allowed me to put things into the field. Oh, it didn't work. Boy, Norfolk Southern Railroad, we went 10 years on that locomotive model before finally getting it to work. And 15 years later, it's still running. Okay. So tremendous thanks to them, but nothing happens without all the students and the staff. This group of people have just been fabulous. I've got a lot of the undergraduate senior theses. At Princeton, we have to do a lot of undergrads, and that's been a fabulous experience. But these were the people who really sat with me through the periods of just not knowing how to write it down, not knowing how to solve it, all of the back and forth. And then at the end, it looks like I know all the answers. Trust me, it is not magical. I have a series of web pages. They all start with tinyurl.com, but SDA Field, SDA Intro, the RLNSO is where my book is. By the way, I have a YouTube video, SDA Field YouTube is sort of a shorter version. You'll see some of the slides from this talk in there. But I'd like to thank, and by the way, special thanks to the transportation science community. Without this community, this was how I got my start. The Journal of Transportation Science was how I cut my teeth on a lot of problems I didn't know how to solve. And I had a community that understood that they were hard, that I didn't know how to solve it, but they didn't know it either. And it gave me that critical academic environment that allowed me to have an academic career, to get tenure at Princeton. I remember TSL business meetings where back in the 1980s, there would be 12 people at the business meeting. It is painful with COVID because, now I look out and there's 150, 200 people coming to our business meetings. This is a really vibrant society. But back in the old days, there was a very small group of us. The field really got going in the 1970s because of Robert Herman, who was a physicist.